If you think AI RAN just means sprinkling AI on top of your base stations, you're already behind. The operators who get AI RAN architecture right will quietly turn the same spectrum, the same sites, and the same hardware into cheaper, more reliable networks, and new revenue from advanced 5G and 6G services. In this video, I'm going to show you the 3 layers of AI RAN architecture, the brutal trust problem nobody talks about, and how this will separate telecom winners from everyone else. Let's start with one question. Why is AI RAN even a thing now? Classical RAN was built to push bits to maximize coverage, capacity, and some notion of average quality. It assumed slow-changing configuration and highly manual optimization. Today, operators are being asked to deliver mission-critical 5G, support complex network slicing, and squeeze more value out of the same spectrum and sites, all while energy costs and SLA expectations go up. AI RAN is the answer to a simple pain. The old way of tuning the RAN is too slow, too manual, and too coarse. We need a RAN that can sense, decide, and adapt continuously at radio timescales and business timescales. Layer 1 is the data foundation. AI RAN starts with the boring part, and that is getting the right signals out of the RAN and the network. We're talking radio metrics, traffic patterns, interference maps, mobility traces, QoS, slice performance, and even external context like time of day or events. If this telemetry is noisy, incomplete, or siloed, any AI you add on top becomes a very expensive random number generator. The real job of Layer 1 is to turn all of this into structured features that models can actually learn from per cell, per user, per slice, per cluster views of the network, updated continuously. For engineers, this means instrumenting the RAN and core properly and building streaming data pipelines. For executives, this is the signal bedrock for smarter decisions on capacity, quality, and cost. Layer 2 is the near real-time brain. Think of a control layer sitting right next to the RAN, often implemented as a near real-time Reki no-RAN architectures. This is where we run xApps that see the live network and make decisions in tens to hundreds of milliseconds. Here, AI RAN decides things like, which cell should this user hand over to? How should we schedule resources between slices and users? How much power should we allocate to different beams or carriers? Every good decision at this layer means fewer drops, more throughput, more stable latency, and lower energy use. This is where the RAN stops being a static configuration and becomes a continuous decision engine. Layer 3 is the policy brain. If Layer 2 thinks in milliseconds, Layer 3 thinks in hours to days. This is often implemented as the non-real-time Reki, or an AI policy engine sitting in the cloud. It watches how the network behaves over time, learns patterns, and then pushes down policies to the near real-time brain. Policies can answer questions like, which xApps should run in which regions? Which slices get priority at which times? Which KPIs like latency, reliability, or energy do we optimize for specific enterprise customers? Technically, this layer uses optimization and reinforcement learning. Business-wise, it's the lever that lets you flip the network between capacity max mode, energy save mode, or premium SLA mode for high-value segments. On paper, this 3-layer story looks beautifully clean. But here's the brutal problem almost no AI RAN presentation is honest about. How do you trust machine learning-driven decisions in a live RAN across multi-vendor equipment, noisy data, and hard SLAs without risking outages or broken contracts? It's one thing to run models in a lab. It's another to let them touch a network that carries emergency services, industrial automation, or high-value enterprise traffic. The short answer is no guardrails, no AI RAN. There are 3 non-negotiables if you want this architecture to be more than a science experiment. First, deep observability. You need continuous visibility into what the models are seeing and doing, like input features, decisions, and resulting network KPIs. Without this, you can't debug, you can't explain behavior, and you can't convince risk-averse stakeholders. Second, shadow mode. Before a new xApp or policy goes live, it should run in shadow, making decisions in parallel without actually controlling the network. You compare AI-suggested actions to what really happened and build trust before you flip the switch. Third, hard guardrails. No model should be able to violate basic safety and SLA constraints. You define hard limits on things like minimum capacity, maximum allowed change rate, or protected slices, and enforce them regardless of what the model wants to do. Let's talk briefly about how operators can phase this in. Most AI RAN deployments won't start with full end-to-end intelligence. Instead, they typically begin with narrow use cases in the near real-time layer, like energy-saving features at night, smarter handover or load balancing in congested urban clusters, and targeted optimization for one or two mission-critical slices. As confidence grows, more data is collected, and observability improves, the policy brain starts to take over higher-level decisions, like which xApps run where, what trade-offs are acceptable, and how to align network behavior with business strategy. Over time, you move from AI helping engineers tune the RAN to AI native RAN as a strategic asset, where architecture and policy are as important as spectrum and hardware. So where does this leave us? AI RAN architecture is not a buzzword layer on top of normal 5G. It's a way of rethinking the RAN as a continuous decision system with three brains. A data foundation that turns telemetry into usable signals. A near real-time brain that acts in milliseconds. A policy brain that thinks in hours and days and aligns the network with business goals. Operators who build these layers with proper observability, shadow mode, and guardrails will quietly outperform competitors on quality, cost, and monetization, often with the same physical assets. Those who treat AI RAN as a marketing term will burn budget, add complexity, and expose themselves to risk without real upside. If you're an engineer, I hope this gave you a clearer mental model for how AI RAN fits into RAN design. If you're an executive, I hope it showed you why AI RAN is a strategic architecture question, not just a tool choice. I'm planning a follow-up where I walk through a concrete AI RAN reference blueprint, including components, interfaces, and example policies, and show how it maps to real 5G and future 6G scenarios. One of those will be 5G mission-critical networks, and another will be sensing-driven use cases. So if you're interested in those, subscribe and stay tuned for that series as well.